Welcome back, everyone. So now that we have understood how to apply product operator calculations to basic modules like spin, echo, inept, and all. So we also did some product operator calculations for depth experiment, right? When we learned spectral editing by NMR. So now that we have learned all of this, we are now ready to take up more complex experiments, like 2D experiments that we have learned in arrayed experiments. So we can now start with heteronuclear correlations and all, but and let us understand how these experiments work. But as we will increase the complexity of those NMR experiments, we will very soon realize that the number of or the product operator calculations becomes increasingly involved. I would not say that these becomes difficult. I would say that the calculations become tedious. The number of terms or the number of operators, density operators, become so large that sometimes if a term is overlooked, one will end up in getting a screwed up result, for example, right? So to avoid such a situation, there is a free package that runs on Mathematica, and so I assume that you all have access to Mathematica. So let us see how to use this package for product operator calculations, and then we will go to 2D applications, right? So 2D experiments. So the package is written for spin half systems, and thus it works very well for solution state NMR. It starts with initiating. So let me pull out one Mathematica file. So let me open up a new notebook, something like this. Okay, so I hope the screen is visible. So now the package starts with running within Mathematica. What you have to do is you have to type this command with double arrows at the start, and then press Shift Enter. So once you say this, you will notice that here the product operator formalism in Mathematica is written, and the package is loaded basically, right? So let me now go back to the notes page, and let us now first talk about all the product operator using Mathematica command. So the name of the package is POMA, product operator calculations using Mathematica. So PO stands for product operator and MA stands for Mathematica. Let us now take a closer look at POMA commands. So first set of commands defines the spin or density operators. And what all do we have? So first is to define the spin system, so which goes with nucleus. Within square brackets you write number 1, and then you define the label of the spin. So this command basically defines that spin 1 is equal to hydrogen. So similarly, if you have spin 2 as carbon or other hydrogen, so you can define a number of spins. So whatever is the number of spins, you can write all these lines one by one. Okay, so that is one. Then second command is spin 1z, for example. So this one is not this will be a square bracket, and this basically defines equilibrium density operator as H1Z. So H is the label which we have defined here. 1 is for spin 1. If it will be spin 1, which is defined by the nucleus 1, if it is spin 1, then spin 2, then it will be written as 2 here. Z is the this variable over here, Z. So if we are defining equilibrium density operator, it will be H1Z. One can also define a raising operator, lowering operator, or X, Y, Z, any of these 5. Okay, so this basically tells you that where are you starting. So generally we tend to start at equilibrium density operator, so we always tend to start with spin 1z, that is I1z or H1z, whatever is the label. So right, that defines your equilibrium density operator. Third is show, and within bracket, and then within curly uh, not quote unquote, so you have label. So this command is used basically to show sigma t in the middle of the experiment. So let's say during let's say after a 90-degree pulse or after a particular delay, you want to know what is the sigma d, what is the sigma t, what is the density operator. So you break the experiment in between and insert this command as show label or show after 90 or show after delay or something like that. We will see the example. So this basically spits out the value of density operator at that particular point where you are inserting this command, okay, in the middle of the experiment. So if you do not do this, then all the experiment is executed once and you only get to see the density operator at the end of the calculation. Okay, so this is just to see what is happening during different steps. So this command, show command, only spits out the value. It does not store that value, but if you want to store that value, then there is a command called store, and you can define it in any way. So for example, if I give variable, then it will store the value of density operator at that particular step in variable parameter. Okay, so stores the value. Okay, so that is one. Then so we had how many? 4 commands listed so far. So fifth is raise lower. Raise lower command is executed like this. So you have 1 2 3 square brackets and inside curly brackets. So this is done to change the basis. So basis set from Cartesian operators to raise or lower operators. See, you can do your product operator calculations in either in I plus I minus format, which is raise and lower operator, or you can do in Cartesian format, which is Ix, Iy, Iz type operators, which we have learned, right? So if you are in this basis set and you want Cartesian, so this is Cartesian basis set, and you want to go to raise lower basis set, so you give this command raise lower. Okay, and if you want to do reverse, let's say, then the obvious command is Cartesian. So 1 2 3 and so on, and this will be the number of spins over here. So in general, we'll be doing our calculations in Cartesian basis sets always. So and if we are starting with spin 1z, so that means we are starting with Cartesian operators. So we do not need these commands because we rarely go from Cartesian to raise lower. So we generally do our calculations in one of the basis sets, right? But you have an option to do the calculations in both. Okay. So Cartesian is to go from raise lower 2 Cartesian. Okay. So then seventh is delay. So delays are very important. So delay is defined by first the time duration, so let's say t or tau, and then it will be defined by what spins are coupled. So for example, this is one spin pair, this is another spin pair, and if there is a coupling between scalar coupling between m and n spins and p and q spins, then all such couplings would come here. Okay, so the format is important. So you have to have the time duration during which the delay is involved or the delay is executed, then during that delay what all couplings are involved. So by default all spins undergo chemical shift evolution. So chemical shift evolution is by default, so you don't need to define that. Of course it has to be non-Z spin, otherwise chemical shift evolution would not take place because the operators will commute in that case. But if it is a non-Z spin, then chemical shift evolution is by default. But coupling evolution is not by default, so scalar couplings are always assumed and have to be defined explicitly. So scalar couplings are to be defined explicitly. Okay, then delay, followed by delay there is a pulse command. So pulse also you need the flip angle. What else do you need? So you need the phasing information. So let's say phi 1, phi 2, phi 3, whatever phase is there, and then it is applied on which spin. So let's say if it's a 2 spin system and we are applying only on one spin, so then you write 1, or if it is applied on both spins you can write 1, 2, and so on. If nothing is written over here, then pulse is applied on all the spins which are available, right? So this is spins, these are the phases, and this is flip angle, right? Okay, so for example, if I'm going to, let me go to new page. So for example, if I'm going to write a hard 90-degree pulse, that is a pulse which is applied on all the spins and it is x phased, my command will be pulse 90x. Okay, so then another command is what was the last command? 8th. Then I have 9th as gradient. So this G, capital G, is the gradient strength. Generally in gradient you vary either the gradient strength, which is as a function of gyromagnetic ratio multiplied, gradient strength multiplied with gyromagnetic ratio, or you change the phase of it, right? So so effect of a gradient on any spin, let's say spin k, is realized as a rotation around z axis by an angle. Let me just write down this statement itself. Effect of a gradient on spin k is realized as a rotation around the z-axis by an angle. Let's call this angle as I don't know, beta is equal to gamma k, G and Z, where Z is the distance uh, at a particular sample slice from origin of the gradient, right? So where gamma k is defined as gk. So this is the Garam-magnetic ratio. Then after the application of a gradient, all transverse magnetizations are dephased. Okay, so if you apply a gradient just before just after creating a transverse magnetization, then all that transverse magnetization will be dephased, as we have learned. And unless you apply another gradient to selectively rephase a particular set of transverse magnetization, if you give a next command which is dephase, it will kill all the uh, uh, discard all the dephased magnetization. So dephase command discards all the transverse magnetization unless it is rephased by an appropriate gradient. So just like there is a dephasing gradient, you can also have a rephasing gradient, as we have learned during coherence selection via gradients. So if you apply another gradient and select a particular coherence, that particular coherence will not be discarded, and otherwise dephase will discard all the transverse magnetizations. Okay. So then after that we have 11th is receiver phase. If we are doing any phase cycling, we have to define receiver phase also. So let's call it as psi 1, psi 2, psi 3 and so on. So this defines receiver phase cycle. Okay. Finally, you have observable. So on what spins you want to put this command, and basically it screens the observable terms which are single quantum, right? So it will discard anything which is multiple quantum or Z magnetization. It will discard those commands, those operators, and it will just keep this single quantum terms. Okay, and also because there are so many operators that have to be applied, so operators when they are applied in succession, they have to be separated by this operator, double slanting lines, forward double slash. So this is to combine two operators applied in succession. So for example, if we have to write f of x, then in Mathematica it will be written as x. So x is the starting point, and then you are applying a function f onto that. So x double slash f, right? So thus we always start with a given density operator, and then so that's like we are starting with I1z, and followed by we are giving a pulse command, followed by we are giving a delay command, and so on and so forth, right? Last will be, let's say, observable. So that's how the sequence of events will happen. Finally, there is a command. This is Mathematica command, simplify. This is not POMA command. This is Mathematica, inbuilt Mathematica command. Simplify is basically to simplify algebraic expressions. Okay, so let us now take an example to understand this further. uh, okay, so let's take an example of spin echo only, because that is the easiest one and we have already discussed it. So let me draw the same spin echo that we have discussed, and then this, right? So you had 90x tau, and where tau is 1 over 4j, let's say 1 2, and then this is 180y. Okay, so if we have this and we are starting with I1z, what is the density operator at this point? So let us try to calculate it using these set of commands. Okay, so let me bring out the POMA page. I hope the screen is visible. So now, as we said, let us start with, after we have called the package, let us start with nucleus. You should see that as you start typing, the command will start showing up. So nucleus 1 is equal to, let's call this as h, and followed by nucleus 2. This is also h. Let's say this is a homonuclear spin system where two spins are h1 and h2. Then let's also define tau delay. So tau delay is 1 over 4 4j, and then the j is between 1 and 2, or the coupling is between 1 and 2. So tau is defined, and then you also defined coupling. Let's say coupling is between 1 and 2, right? And that is all, because there are no phases. We are not doing any phase cycling, so we don't have to define phase cycling at this point. So we will see more complex examples once we will look at the phase cycling. Once we will have the phase cycling. So for example, in 2D correlation experiments, we will do it with and without phase cycling, and then we will see the difference. Okay, so this basically defines the spin system, that there are two spins, both the spins are hydrogens, then there is a coupling present between the two spins, and the tau period is equal to 1 over 4j of the two couplings. Okay, so then let's define the equilibrium density operator. So spin 1z, that's the point where you want to start, followed by 2 backslash to give you to connect you the next set of commands. Now followed by this will be, so I'll just break it up into next line. Okay, so next will be pulse, and the pulse is 90-degree pulse, which is a x pulse and is applied on both the spins, followed by again double slash. Then after 90-degree pulse, so you have a delay, and that delay is for tau period, and during the tau period coupling has to be evolved, right? And after that you have pulse, which is a 180-degree pulse with y phase, and this is also applied on both the spins. Then you have double slash and delay again. This delay is again tau delay with coupling being evolved. So again, chemical shift evolution during these delays is by default, although the overall chemical shift will be refocused. We will see that later, how chemical shift terms will come and then they will disappear later on, as we have learned earlier. So then the delay is over. Yeah, that is all right. And then we will say observable, just in case. Now after observable, so you have to press shift enter to execute the cells, and as soon as you do that, you see that it does some sort of calculation, and basically the same calculation that you have been doing by hand, and then it spits out the density operator as 2h1x h2z. That is the antiphase term in spin 1 with respect to the second spin, right? So 2h1x h2z, but it does not tell you how the spins or how the density operator has evolved. So if you want to do that, if you want to see how the density operator is evolving, what we can do is we can invoke the show command, and we'll keep on writing whatever we want in between. So for example, this is equilibrium density operator, okay, and then again we will have double slash again, so show after 90. Okay, then after we can say show after first delay, or after first tau we can say. Then again not show here, then we will say show after 180. So do not forget to put these forward slash, otherwise the commands will not execute, because it will be seen as a broken pipe or broken set of commands, so it will not be executed. Then show after second tau. Then observable, right? Okay, so I think that is all. So now if I press shift enter, now you will see that it tells you equilibrium density operator. So it still does the same calculation, but it will break the calculations in between, and it will show you how the spins have been evolved, or how the density operator has been evolving. Okay, so for example, equilibrium density operator is h1z. After 90 degree pulse, you convert it into minus h1y, right? Then after first tau, so now you will notice that there is sine omega 1 by 4j. So there is a omega 1 modulation coming with h1x term and h1y term, and the corresponding antiphase terms also. Because initially there would be a chemical shift evolution of h1y term, right? So, and then there would also be a coupling evolution with respect to spin 1 and 2. So that, because now the period is 1 over 4j, so it will amount to cos 45 and sin 45 terms, which are 1 by root 2. So 1 by root 2 is coming in all of these. So here it is 2 by root 2, because 2 comes with the antiphase operator. So 2 by root 2 will be root 2 in the numerator here, root 2 in the numerator here, right? So after you apply 180 degree x, 180 degree y pulse, it will convert hx into a negative sign. So you have a negative sign here. Then hy term does not change, because 180 degree pulse was the y phased pulse. So similarly, h1x, h2z, both of them will be negative. So this sign remains same, and then h1y remains same, and h2z goes to negative. So you have plus to minus, right? Then after second tau, if you see that the chemical shift is now refocused, the coupling has evolved, and that's how you also have h1x, h2z term now. So you started with h1y before tau delay, and now you end up in h1x, h2z, right? So, and that is like, if you type observable, it does select this, because this is a single quantum antiphase term. So this is your final density operator. And after this, if you do a T1 evolution, so I have not done that, so I have not written that in the pulse program here, that I am going to detect it. So that's why I have not done. But if you want, what you can do is uh, after observable, you can have another delay which will be a t1 delay, and during which the coupling will be evolved. Right? And now if you shift enter, you will see that the antiphase term will now be evolved into a so there would be a chemical shift modulation, so omega 1 t1. So basically h1x term will have omega 1 frequency, and you will see that there is also a coupling term which is coming, right, sine pi t1 j12 and so on, right? So all those terms, so you can now this is your final density operator, which you can take a trace with I plus operator and find out the complex signal, right? So why we are discussing this is it does make your calculations very easy to understand, and also it gives you a feeling of how to write a pulse program in a code. So because typically when you are let's say you're sitting on the NMR machine and you are actually trying to understand an experiment, so there you will have to learn you'll have to understand the pulse program in a code which is written in some programming language. So for example, in variance spectrometers it used to be written in C language, but in Bruker spectrometers it is written in Bruker's own language. But it is very similar to understand that okay, you have a pulse followed by a delay followed by something else. So all sorts of commands have to be written one after the other. In the very similar fashion, Mathematica also does treats the pulse program in a similar way. However, this is much more simplified version of what a Bruker pulse program would read like, but it definitely give you some idea of how to write step-by-step instructions for a given pulse program and see how the calculations are changing and how the density operator is evolving. So that is all for today, and let us take more examples using product operator calculations in Mathematica for 2D correlation experiments. So we will take up examples with and without phase cycling. We'll also take up using gradients, see how to apply gradients in these type of commands, and see how the density operator is